हे आपका फ्रेश कोडमैन में स्वागत है। और आज के दिन वी विल बी लर्निंग अबाउट द ग्राफ्स। सो फर्स्ट ऑफ ऑल वी डिस्कस व्हाट इज ग्राफ इज, then we'll see how can we create a abstract data type for graph, and then we'll solve some of the questions based on the graph. So that is the aim for today. Let's start without wasting our time. Okay, so here we have this. Okay, so what is graph is? So graph is a data structure that generally uh, used to represent the uh, connected node with the vertices that span in complete 2D diagrams. Okay, so interrelated data are represented by the graph. That is the main important thing. Like if you talk about the friends relationship, okay, so friend is a node and relationship is a edge. So based on relationship, one friend can have many, one friend can have one f can have f1, f2, and f3, and these are the relationships. So these are the edges, and these friends also can have some other friends like f through. So this is a graph. So this way the graph spans. So there is no limitation to it. How many nodes, how many edges. Just the thing is, uh, if a data structure has a node which can be connected to the other nodes with the edges, that is called as graph. Simple as that. Okay, so let's discuss the nomenclature terminology is about. So what is a node? Node represents in a graph. This particular thing is called as node, and to connect two nodes we use the edges. And if a node and adjacent nodes, so nearby nodes, if I'm talking about the f1 here, so adjacent nodes will be the nearby nodes like f3, f1, and these will be the adjacent nodes. And yeah, so this is the adjacent node ho gaya. And then let me see what we need to define now. Okay, define graph, node, vertices, digraph. Okay, so there is a concept of digraph also. If you see, digraph means directed graphs. So this was a, like, if you see, look like a friendship. So friendship is a two-way thingy. So if this person one is your friend, then he is also your friend, and you are also his friend. So there is no direction to it. But if you talk about the if you take in some other example where you have this only direction thing, like transportation, you might say, if there is a one-way road only. So in that case, if there is a okay, city 1, C1, C2, C3, C4. So now if I make a diagram and there is only one way is there, so there is only possible to reach the C3 by going C1 to C4, C4 to C2, C2 to C3, because these are the directed graphs. The person who is going from C1 to C4, he cannot come back here. He cannot come back to this C1. So that is the problem with it. So these are the directed graph. The direct graphs are those which have the edges with the direction. Undirected graphs are those which have the edges without any directions or yeah, anything. Okay, let's see what is the next. Next is degree. Okay, degree path cycle type. Degree path cycle type. Okay, cool. So degree is, uh, if you see this diagram, and if I take an example of C2, okay, then I will say the degree of C2 is Okay, let's take an example of undirected graph first, then we'll go to the directed graph. For undirected graph, degree is the number of edges connected. So F3 is connected to the one edge, two edge, three, four, five edges. So degree of F3, degree of F3 equals to 5, but that is for the undirected graph. But if you have the directed graph, then degree is two types: incoming degree and outgoing degree. Okay, so C2 have one incoming degree because one edge is coming from the C4, so one incoming degree and one outgoing degree. Or maybe if C2 is already connected to the multiple of them, like C5 is also connected, and C6 is also connected, and C7 is also connected, and now it is incoming degree but others are outgoing, then C2 will have two incoming degrees and three outgoing degrees. So this is about the degree. And then path. Okay, path is a series of connected nodes which all of, okay, it is a two connected nodes via some other nodes and using edges. So if you talk about the C6 and C1, so the path to C1 to C6 is, it will become like this. It will go through C4, C2. Okay, there is no path to C6 by the way, because it is just a directed graph. Maybe C3 के लिए we can look. So this is a path. So path is a uh, connected edges to any two nodes from one, if you can reach from one nodes to the second node. Simple. It's just a path. And then if you talk about the loops, if if there is a node which is connected to itself, like similar ways this way, if it is connected to itself, that is called loop. And if in undirected you talk about, so if it is connected to this way, then it is loop. And now let's talk about the cycles. And suppose we were here and this C3 got connected to get connected to C1 again. So what is happening is, if it is a path which starts and end at the same point. So if we have a C1, it's start from the C1, C4, C3, C3, and then again ends at the C1. So that is a cycle. Okay, let's see the next thing. What is upcoming? Types of graph. Okay, so already we discussed about the there are two types. Mm, digraph, directed graph, undirected graph. We already talked about direction or indirection. Then cyclic, acyclic. Cyclic we already talked. If a graph has at least one cycle, then it is a cyclic graph. If it don't have any of the cycles, then it is an uncyclic graph. If a graph don't have any cycle, okay, cool, that's okay. And then you have a weighted graph. Sometimes what happens, like if you take an example of transportation itself, it's a good example for this. So suppose you are going to, there are multiple paths to reach the one, two, three, four, five, fourth city from one. Okay, then you might reach 5 also. So there is multiple path to reach the city 4, but if you see, weightage for one is 1, weightage of this one is zero point 0.5, weightage of this is 2, this is 2. So which path will you took? The path we will took is like looks like we will took straightforward with this 1 to 4, right? It's look like that, but we don't. Why? Because weightage is very less. Maybe there is something wrong with this path. So that's why we will pick the path which has the higher weightage, and we'll calculate that in some other fashion. So we might be taking the path 1 to 4 or something like that. Or if it is a 0.5, then we will definitely 1 to 2, 2 to 4. This will we going to pick. So If the edge have some weightage to it, then it is weighted graph. If don't, then they are not weighted graph, unweighted graphs. Hmm. Okay, cool. And then we can move to the next type of the graph. What is the next type of graph? Adjacent node digraph, all of them is happened. Okay, then undirected, directed, weighted, unweighted, cyclic, acyclic, connected. Yeah. So there are this connected graph and yeah, connected graph. So it might be possible you have multiple graphs like this whole thingy, this whole particular parts thing, this whole thing. This is a single graph, but if you see there are sub graph which are not connected. So if you look closely, this graph and this graph and this graph, three of them are isolated to each other and they are not connected at all. So this is a disconnected graph. If a graph has any two subgraph which are not connected, then it is a disk graph. Sorry, not disk graph, disconnected graph. Okay, and connected graph. If a graph which don't have any of the graph which is not connected, then it is a disconnect. It is a connected graph. Now, if you see closely, you might find that if you take a graph which is acyclic, acyclic, connected, connected, and and connected and undirected, undirected graph, what it is going to become? It is a tree, like, okay, it is a tree. So if you see this way, then it is a tree. Why? Because how tree looks like, you will the tree looks like you have a node, it is connected to some other nodes in a some fashion, right? And it start or ends somewhere. So if it is a cyclic graph, then it definitely be starting from somewhere. So this is a tree itself. So if a graph is acyclic, connected, and undirected, if it is have two isolated island, then it won't be a tree. And undirected, like, okay, it is not directed, it is undirected. The person can go in anywhere in the direction. That is the tree, right? Okay, let's see what is remaining. Disconnected graph. Yeah, disconnected is unidirected acyclic. Yeah, unidirected acyclic. Undirected acyclic graph. A graph that is not directed and don't have any cycles. Directed acyclic graph. DAG. Mm, Directed graph which is acyclic is directed graph is DAG. One important property is DAG is that they are topological sortial items in the vertices. I don't know what it means, but yeah. Okay. Real world application. I already told you social media applications. Social media applications, two friends, it's the same example as the friendship because the social media already always use that particular thing. So they store the data in the graphs. If this person is connected to the other person and the other, okay, that is the thing. Recommendation system also use the graphs. It checks some of the properties and based on them it creates a graph like at which level a person can reach. That is the thing. Compiler, network routing. So network routes also uses the graph. Okay, now we'll reach the graph representation. Up until now, we will just discuss what are the graphs. Let's see how to represent the graph itself. Okay, okay. There is a two ways: matrix adjacency, and list adjacency. So matrix, it's pretty simple. Okay, if you see the graph, how it look likes to you. So if you see a graph, you will see, okay, there is a node that we call as vertices, and there are edges. Those are edges itself. And when we do it, so there is some kind of relationship between two nodes. If I create some kind of matrix where I put all the relationship with these vertices, then it will show us this thing. Yeah, same thing we'll do in the matrix representation. Suppose we have a small graph, once it 0, 2, 3, and this. We have this undirected graph. So which have 1, 2, 3, 4 nodes. Then 0, 1, 2, 3, 0, 1, 2, 3. Okay. Now we can write down the if it has the edge or not, and based on that we can create the graph itself also. Now, if you see 0 to 0, do we have any loop? No, we don't. And then do we have 0 to 1? 0 to 1. 0 to 1, yes, we have. Okay, यहाँ पे अपन सही का निशान लगाते हैं. Yes, we have. Then 0 to 2, no. 0 to 3, yeah, we have 0 to 3. Yes. 1 to 0. Yes. Okay, let's make a directed graph. So it looks good. Okay. Now it's cool. So earlier 0 to 0, 0, 0 to 1. Yes. 0 to 2, no. 0 to 3. 0 to 3, no. So यहाँ पे no हो जाएगा. Okay. Then 1 to 0, no. 1 to 1, no. 1 to 2, yes. 1 to 3, yes. 1 to 0 और नहीं है. So 2 to 0, 2 to 1, 2 to 3, 2 to 2 and 2 to 3. And then 3 to 0 ही है, उसके अलावा कुछ नहीं. तो 0, 0, 0, yes. 3 to 0 है, सॉरी. 3 to 0 है. 3 to 0. Okay. 0 to 3. 3 to 0, yes. And then 0, 0, 0. No, nothing, I mean. No, no, no. Okay. So suppose if I hide this graph, can I be, will I be able to create it now? Yeah, I'm sure. So we will create, we have 4 nodes. Okay. So 0 to 0, no. 0 to 1 we have. So I will create a 0. I will create a 0 and then create a 1. Okay. And this is the direction to this. And then 0 to 2, no. 0 to 3, no. 1 to 0, no. 1 to 1, no. 1 to 2. 1 to 2, yes. 1 to 3. 1 to 3, yes. And then 2 to 0, 2 to 3. 2 to 3, yes. And then 3 to 0. 3 to 0, yes. फिर उसके बाद कुछ नहीं. So we have created exactly the same graph. So this is how we can do it. Sorry, I was not showing you, but I created this matrix here. So based on this graph, we created it, and now we are doing it. Cool, no problem. You can miss this part, move to the next one. It's okay. Yeah. So this was the matrix representation. Let's move to the other representation, that is the list representation of it. List. So in the list representation, what we will do is we will have all the nodes in the list like 0, 1, 2, 3, and store the edges here. Okay, so zeros के साथ which edges we have? 0 to 1 we have. Yes, 0, 1 we have, and then nothing else, right? Yes. Then 1 के लिए what are the edges we have? 2 we have, 3 we have, 2 we have, 3 we have. Okay, 1, 2, 3. 2 के साथ we have 3, and 3 के साथ we have 0. So this is the representation. What is the benefit of it? The benefit of it is that it is more compact and uses less storage compared to this. If there are like 10,000 nodes in this graph and they only connected to the one node, then what will be the space complexity for this? This one will become 10,000 multiplied by 10,000, because it will need this much space, but for this one it will like 10,000 multiplied by 2 only, because one for the node, one for the edge connected to it. So that's why it is efficient in space. Okay, cool. Now we can start modeling it. Graph representation is done. So here we have our first question. Okay, cool. So now, yeah, we can do some things here, by the way. Yes, let me do that. Yeah. So here we will be doing basic representation. So what we will be creating is we will be creating abstract data type. So what is the abstract data type? Abstract data type for graph is it will show only the graph functions or and hide all the complexity whatever happening at the backend or its core. So we will create a class that called as graph. Okay, and this inside the graph, what we will do is we will create some of the method like add vertex, and all the methods are listed here. If you see, I can copy all of them. Okay, and we will discuss them one by one. Okay, now you will see all of them. Now we have the adding a vertex and removing a vertex and all of them. So if you talk about the adding a vertex and which representation we will be using, we will be definitely using a uh, list representation of the graph. Okay. So now adding a new vertex, it's quite simple. We will, if it is a new vertex, that means, okay, first of all, how we will going to initialize it? Because list will be a map of the nodes. So nodes or vertices. So vertices can be easily be searched. So we will create a map, okay, in the constructor. Constructor में we will create a map or that will be called as graph. Okay, so it will be a map, new map, and now okay, now if we need to add a new vertex, we will check. If present, so don't add it. If not present, then graph में node add करें and equals to empty array, because this array don't have any of the this vertex don't have any of the relations up until now. Okay, then removing a vertex, that's okay. Suppose you have a graph already created where you have v1 as a vertex 1 which have this v2 v3, and then you have v2, and then in the v2 we have v3, and yes, and then you have v3, inside that you have v2. So this is the diagram you already have, or this is the graph you already have. Now he is saying remove v2. Okay, so first thing we'll definitely do, we're going to remove this complete relationship. Okay, then we'll definitely remove these relations also by going through all the vertex one by one. So this is our task. So removal में क्या करेंगे? Remove vertex and remove all relation with others. That's will do. And then adding an edge between two vertices. Okay, it's just pretty simple. If the if it is saying add a vertex between v1 and v4, first of all we will check if v1 exists or not. Okay, let's create a existing ones के लिए v1 and v2 के लिए create करना. What we will do, we will see if v1 is exist in the graph or not. If it is exist already, if it exists already, then we'll add just v2 into the array, push the v2 into the array if it is not present, or we can just push it. Yeah, it's okay. Or maybe we can just create a sort, sorry, oh. It is called as sets. We will create sets instead of array. So we don't need to worry about the duplication. Yeah, that's good idea. I like that now. Okay, so V1 के लिए if V1 don't exist, then what I'll do is I will add V1 vertex here, then add V2 into it, and then again I will check V2 exist or not. If V2 also don't exist, or if it is exist, then V2 के उसमें हम V1 डाल देंगे. Pretty simple. Okay, this was the adding a edge and removing an edge between two vertices. Okay, suppose now he is saying V2 से V3 की vertex हटा दो. This one thing he is trying to say, remove it. Okay, now it's about the undirected or directed graph. Right now we are writing for the undirected graph, so we don't care about the direction. Do we care about the direction or not? Removing an edge between two vertices, getting list of all vertices. Okay, cool. हाँ, we are not worried about the direction right now, so we will सिर्फ remove कर देंगे. So we will see V2 से V3 कहाँ पे will remove it, and V3 से V2 कहाँ पे will remove it. Both of them we just remove it. Them. If they don't exist, so it's okay, no problem. Getting a list of all vertices is pretty simple. Just give them this. Getting if two graphs nodes are adjacent to each other or not. Nodes are no two checking if two graph nodes are adjacent to each other. No. Okay, if it provides us v1 and v3 and want to check are they adjacent or not, then what we will do is we will check. Okay, v1 के neighbors में v3 exist or not, or v3 के v1 में exist or not. If they are adjusting in the edges, that means adjacent nodes, that means, yeah, that means it is a neighbor. Getting count of total edges in the graph. Total edges in the graph. Okay, that will be the count of number of all of these. That will make a edge. Getting a list of graph edges. List of graph edges. Okay, it will create v1 c v2. Okay, we can do that. Getting neighbors of the graph. It just print these. Okay. Okay, do I just make it? Okay, now it looks like we can do it. Let's do it. I'm just implementing it and then I'll show you. Okay, cool. Okay, so finally we have implemented the solution here. So if you see this, we have a graph that have this adjacency list and we are adding a vertex. If the vertex is not present, then we'll create a set adjacency list. We are not using array, we will be using set because it is good. It improves on duplicacy. Remove vertices, and if not a vertex, it is not present, then you can't remove it. So graph is not found, and similar ways we did all these. Okay. So let's move to the next problem of sorts, and that is about the traversing it. And what is the traversal? Let's see that. So whenever you solve a problem in the problem solution, what you do is you need to traverse all the nodes similar ways we do in the arrays, we do in the linked list, and everywhere we do the same thing, and we traverse to the all the nodes of them. So in the graph, if you see a graph, as here I'm creating one 0 1 2 3 4 5. This is connected this randomly. Okay, so now the question is how can you uh, traverse the whole graph? That is the aim for today. So traversing a graph is there are two ways to do that: depth first search and breadth first search. Okay. So depth first search means uh, you are going into the depth of the graph up until you reach the same node or same vertex, or you need reach a like leaf node. Okay, so similar ways, suppose we start from the 0 here, and then this suppose our head right now, and if we start from this and we say okay, let me traverse it. So to traverse this we use generally stack, and these stacks may we push the values. Okay, so suppose we are starting from 0, so we push 0 here, and then we pop the 0 and add all the mm, all the nodes which are adjacent to it. So all which one are the adjacent? 3 is adjacent, 4 is adjacent, 1 is adjacent, and then let's assume this is a 5. So 5 is adjacent. Okay, so all of them I put. Now I will say okay, this is visited now. It might be possible we have cycles, loops, and so on and so forth. So we need to have to track, is this node is visited or not. For them we will be using this flag, visited flag. Okay, then now we'll this 0 is we pop the 0. Now we have 3, we'll reach to the 3 and then pop the 3 out of it, and we are here now. So now at the 3, if you see, is there any adjacent node? No. So we visited it. Okay. Then we go to the 4. Let's assume 4 have more nodes, like 6 here it is. So it makes sense to us, right? So 4 we already traverse. Then what we'll do? We don't visit the we okay. We don't visit the 4 up until now because there is an adjacent node. What we'll do? We add the adjacent nodes to it. Okay, adjacent node is 6. It got added because in the stack, first in, first out. Hmm. So sixth is got added, and then we reach to 6, and then we'll say, is there any adjacent nodes? No, not yet. So what we'll do? Okay, there is no adjacent node. Then we'll say, okay, this is visited now, and then we'll remove this. Then we'll go back to the fourth one. We'll say, okay, this all of the nearbys are visited. Then we'll say, okay, this is also visited now. Remove the 4, and then we go back to it. Now it will reach to 1. Okay, and then in the 1 it will see, is there any adjacent nodes? There is 5, we'll add 5. Then there is 2, then we'll add, sorry, not 5, won't be going there. Yes, 5 will add in the stack, no? Yes, remove all of them, and then we'll see. Okay, 1 is there, then we'll add 5 here and then 2 here. Okay, so then it will check. Let's see the 5. 5 have the adjacent nodes like 2 and 1, but those are already visited. These are, this 1 is visited, but 2 is not visited, right? So it will reach to 2 and add the 2 here, and this is now visited, and we'll pop it up, and we reach to 2. Now this is visited, we remove 2, and then 1 is already visited, 5 is already visited, nothing is there. So now our stack is finished, and we visited all the nodes. So this is the depth first search, and then we have breadth first search. Breadth first search may we'll use the queue to track the all the unvisited neighbors, similar to the tree. Both the cases are exactly same. Let's see how we use them to create a, let me create one algorithm so such that we can traverse all the nodes one by one by using both of the techniques. Okay, let's see. Okay, cool. So now we have the solution here. The solution goes like this. So this is BSF, DFS. So in DFS, what we will do, I said you, we will create a stack. We will create a visited. Visited, I'm creating as a map. So the deletion and like the addition to the map is quite easy because we just need to visit them. So stack, may we put the first node, that is the starting node, and then we are saying while stack length, if the stack has some length then it will run forever, if the stack is empty then it will stop, and then we are popping the first node, that is the starting node now, right now, though that become node, and then if the node is already visited, then we don't do anything, like we don't print. If it is not visited, then we say ki, okay, now we are visiting it, and then visited dot set node true, we'll set it as a node true, and we'll add the adjacent to the stack if they are not visited. Okay, and that's it, nothing more, simple as that. Okay, cool. Let's look at to the BSF, breadth first search. In the breadth first search, what we'll be going to do is it will be searching level wise, and we will using the queue similarly to the as we did done in the tree traversals. It will be the similar to that. So we will be creating two things similarly, visited and the queue. So visited, it will be the new queue which have the V vertices, and then queue is queue. Okay, now I'm not creating map. It's okay. We can create an array also because all the nodes are just a 1, 2, 3, 4, 5, like 0, 3. This is okay. Then visited start vertex is true, and then queue dot push start vertex. So we pushed the start vertex in the queue. Then while queue dot length is not equal to 0, up until we run this thing, we uh, we remove or we pop the first or dequeue the first one, so q dot shift current vertex, and then we'll pop print it, and then for constant neighbors of this adjacent list we will push them to the queue. If not visited, then we'll say visited neighbor barabar true, q dot push neighbor. Okay, so we'll say them ki they are visited already, and then marking them true. Or visited means they pushed to the queue, and visited means they pushed to the stack. That is it means only. So cool. If we run it, it will goes like this. So it will go to 0, then 1, then 2, then 3, and then 4. But earlier what was happening? It was 0, 1, 2, 4, 3. If you go back and then see 0, 0, 3, 2, 4, 1. Okay, cool. Yeah, this way it was happening. And now we can move to the first problem of today. The first problem of today is find if path exists in the graph easy. Okay, easy problem hai. In given an undirected graph represented as a list of edges, each edge is illustrated as a pair of the integer u and v. Okay, signifying that there is a mutual connection between node u and node v. Node view and you node v. You are also given starting node start and the destination node end. Return true if a path exists between the starting node and the destination node, otherwise return false. Okay, if the path exists, then else it's okay. Then what we will do is for this one we can use anything. It's okay. We can use BSF or DSF, DFS. Doesn't matter at all. Both will work here. And then it says input is 4. Edges are 0 to 1, 1 to 2, 2 to 3. 0, 1, 1 to 2, 2 to 3. Start is 0, then 3. So executed output is true. Justification, there is a path from node 0 to 1 to 2 to 3. Okay. Hmm. Okay, so we need to, okay, we just need to tell ki path is exists there. We don't need to say anything at all. So we have start and end and edges and n. Oh, it's saying ki we need to create a map out of it, and then see is that exists or not, that path exists or not. Hmm, okay, we'll do that. No problem at all. We'll do that. No problem at all. Edges are 0, start is 0, end is 3. Start 0, 3. 0 4. Okay, constraint edge length, edges 0, source 0 or less than greater than equal to source destination is this. There are no duplicate edges and there are no self edges. Okay, cool. Now we get this problem. What we need to do to solve this problem is what I'm thinking right now, because we are reading the graph. First thing is clear, we will be creating a graph out of it. Is there another way we can solve it? Mm, there is one other way we can solve it, definitely. What we can do is we will start and end we know. So we'll search the zero in all these arrays, these edges. If we find the zero somewhere, anywhere of them, then what we will do is we start looking for the next one in the other ones, but it will be quite long because for all of the zeros I will be looking for all of the other ones. But that might take like n to the power n. Yeah, that is the possibility. But that is pretty long. So what we'll do, we will create a graph and then solve it. Okay. So what I'll do, I'll create a graph first of thing. Graph. Okay. And the second step will be use okay, let's use DFS right now. DFS to find the okay start node I know. So to I will search from start from the start. Okay. So start with start node and search for end node. Okay. Using DFS. If it exists, then true, else false. This is our algorithm. Or yeah. So give me time. I'll just do it. So here we have the solution. So what we did exactly, we created a adjacent tree in these lines. If the edges are not present, that means there cannot be any path. So return false, definitely. And then we created adjacent list as a map. If this edge ka first or second uh, vertex are not present in the edge list, then add them and initialize with the empty set. And as they are there, we can add the adjacents to them. So 0 ka adjacent 1, 1 ka adjacent 0, so that we are getting and adding them to it. Okay. And then now we have created the adjacent list. Now we can traverse it by the DFS. We have created a stack as we discussed earlier. Visited stack में start को push करा and visited to set to start. Okay. Then when stack dot length है, then we'll say current को pop करो. अगर we get the end, then true, नहीं तो मत. Okay, cool. So this way we found the solution. Let's move to the next question and let's see their solution, by the way, how they are doing it. They have the constructor this dot visited valid path. Okay, do I had that? I don't know. For let I barabar 0, graph I, initialize the graph, initialize the graph. Hey, why are it is doing the same thing multiple time? Don't know. Maybe we missed it. Okay. Populate the graph from the edges. He is populating the graph. Oh, he is using a matrix representation here. That's okay. Whatever it is, it's okay. We can move ahead. Problem statements. There are n cities. Some of them are connected in network. If city A is directly connected to a city B and city B is directly connected to city C, city A is indirectly connected to city C. Yes, correct. If a group of cities are connected directly or indirectly, they form a province. Okay. So given an n cross n matrix is connected, when is connected ij is 1 if ith city and the jth city are directly connected. and is connected 0 otherwise. Determine the total number of provinces. Okay, nice. Okay, nice. So what we can do to solve this problem? Interesting problem though. Huh. Let me give you the solution, walk through how can we solve it. Okay, for that we need to open and move to the other website or page. Okay, and then follow the Vizanalam so he can tell you the some things. That's me though. Okay. Okay. So it's saying ki we have like this way of the kind of something like this, right? And he's saying we need to find the total number of province. What we will do is we will have a matrix, some kind of this, and we will create a visited node. Okay, and we use DFS or BFS here, doesn't matter. So we this way, this time we use BFS, last time we used DFS, so this time we use BFS, and pick one node. And first of all we use a for loop to iterate all of them, all the vertices. We iterate all the vertices. If maybe there are some vertices which not okay, and then we go to the first one, and then look for all the nodes, linked nodes to that. Suppose this is 0 1 2 3 4. Okay, so here is 0 1 2 3 4. We start with the 0th one, and then we do BFS on it. So it will, this will be visited, this will be visited. Yeah, and then check. Now all the nodes are finished for this province. Then we count, okay, one province, and then we will move ahead in this. Okay, then we'll see. Okay, one is already visited, so we don't do depth first search on this. Then we'll go to the two is not visited. Then we'll definitely know, okay, there is some other island where this two city is present, and because it is not visited, then we'll do the depth BFS, breadth first search for the two, and then it will make all of them visited, and then we mark the, okay, now the total province become two. Okay, total province become two, and then we say, okay, move to the three, move to the four. Cool, there is nothing else, we are done, province are two, return them, simple as that. So what we'll do, we iterate the vertices. If they are not visited, then we'll do the depth first search using stack and everything. And after depth first search, we'll say, okay, now we got the one province. We increase the count of the province. And after this depth first search is done, province count is increased. Then we'll repeat this process multiple time until we visit all the vertices. That is the solution. Let's see how I'll going to solve. So here is the solution for that. We were saying we will create a for loop to iterate all the cities from 0 to end, and then we can remove this and remove this. Okay, and then if the city is not visited, then we will do the depth first. Okay, BFS, breadth first search. This time we are using a queue, pushing the city, marking it as visited, and then doing a breadth first search. And after the completing the breadth first search, we visited all the cities on this particular island, and then we'll say, okay, now the province is one. We found the one province, and then we go through the for loop. If that city is not visited, then we'll again do the breadth first search, and then this way it will going to do it. Okay, and we submitted it already. Let's see their solution, how they are solving it. Okay, they created a union find constructor, something union set solve find province. They have for loop for j to this, and then if is connected wherever one, so you have find find a number of provinces and guys, I don't know what they are doing, but okay, maybe they just explained it a bit here. Initialize, create a union find data structure with parent and rank array. Initialize the parent array in such way the on parent initialize process for the connection algorithm work through. They are using something else, uh, but we used it by the graph. That's okay, no problem. Let's move to the last and final question for today, and that is a minimum number of vertices. Let me see how many questions are remaining on this. Yeah, minimum number of vertices. This is the last one. So minimum number of vertices to reach all nodes. Okay. So given a directed acyclic graph, acyclic, there is no cycles graph with n nodes labeled from 0 to n minus 1, determine the smallest number of initial nodes such that you can access all the nodes by traversing edges. Return these nodes. What do you think? Given a directed acyclic graph with n nodes leveling from 0 to n minus 1, determine the smallest number of initial nodes such that you can access all the nodes by traversing edges. Return these nodes. Okay, minimum number of nodes we need. Yeah, कि सारे के सारे को अपन एक्सेस कर पाए. That's what. Okay, now this graph is directed, a cyclic directed graph. Okay, now it's cool. Hmm. So we at least need 0 to reach 1 and 2, and then 3, 4, 5, 6, 2. This is how we can reach. Hmm. So this is the graph. Okay, interesting one. Interesting question. Interesting question. There is one way. First way is, let me show you how I'm thinking about this. Okay. If you see here, initial, the first solution that might it can be this way also. That says, mm, suppose you have this. Okay, this is acyclic now. So we need to create a acyclic directed graph. Okay, let's do that. Okay, this is our graph 0, 1, 0, 1, 2, 3, 4, 5. So here we have it. What we can do, we again traverse all the nodes. Traverse, that is the brute force solution most probably. So traverse all nodes. When you traverse all the nodes, what will happen is, and then try to create count of province, and if the count of province is less in one of them, then set that to the right. But it will take a lot of huge amount of calculation. So first thing is, it